So now let's experiment with this code a little bit. Everything is ready now. So we have a system where we can define who are the initial adopters of the action A, and then we can run the code and see how this action A is cascading in the network, whether it dies away or whether it persists in the network or what happens. So for the time being, what I'm going to do is I'm going to set the initial adopters to be 0 and 1 in the network, and I'm actually also going to change our payoffs associated with A and B. So let me keep the payoff associated with A to be equal to 6 and with B to be equal to 5. And let's execute this code and see what's going to happen. So initially 0 and 1 in this network have adopted the idea, and then you see it dies away. So seems like the payoff 6 is not enough for this action A to cascade on this network, right? So what I'm going to do is I'm going to increase the payoff, and I'm going to keep this payoff to be 7. Let's see what happens now. So when I keep this payoff to be 7, initially 1 and 0, and then again it dies away. So the payoff 7 is also not working. Let's make it 8 and make it 8, and then we have 0 and 1. In 8 also it dies away. Okay, let's make it 9. Dies away, and let's make it 10. And then you see when I make it 10, now although 0 and 1 they have adopted the behavior B now, but these three nodes 2, 3 and 7, they have adopted the behavior A. So the behavior is persisting. Let's see in the next iteration. In the next iteration, now 0 and 1 also get back the behavior A. So now you can see this behavior A cascading on this network, and then you see some more nodes adopt the behavior A, and then finally all the nodes adopt this behavior A and the process ends. So have you seen just now what happened? We have started with a payoff 6. So when the payoff was 6, nothing happened. 7, 8, 9. The behavior A ultimately died away, but when you made its payoff to be equal to 10, everybody in this network adopted the behavior A. Let's try doing something else also. So let's make it 6 and 5, and let's change my initial adopters to be, let's say, 4 and 1. And let's see what happens now. 4 and 1, and then 6, and then dies away. Okay, let's increase the payoff to, let's say, 8. 4 and 1, 6, dies away. Let's say 9, 4 and 1, then 6, and then dies away, and then 10. Okay. Do you see here what is happening now in this case? So this was what I wanted to show you. In some situations, what can happen? You see 7, 6, and then 7 and 6 infect 4, and then 4 infect 7 and 6, and then 4, and then this, and then this, and this code goes into an infinite loop. And it's going to run 100 times. It's going to run 100 times. Okay. So what I want to do is, instead of seeing this code to run for 100 times, I actually want to know just a simple thing. I want to know whether my cascade is complete or not. What do I mean by my cascade is complete is everything at the end has adopted this behavior, which is behavior A shown in green color, or not. So that is my only aim. So I don't want to see these intermediary graphs. So I just want to see my graph once at the starting, once at the end, and in addition I want to know whether my cascade is complete or not. So we can quickly see whether my cascade is complete or not. So we call a function C here, variable C here, which holds the value, is my cascade complete or not, is complete cascade. So whether this cascade which has occurred on my graph, it is complete or not. And how do we know it is complete? Okay, so you see we have used this function here, terminate 1 ag. So this function, it used to return 1 when everything in this graph has adopted the behavior A. So instead of using a new function, we can use the same function. So we can use this function terminate 1 ag, which tells me whether all the nodes in my graph has adopted the behavior A or not, right? So what I'll do is C equals to terminate 1 A comma G, and what I want to see is I want to print. So if your C equals to 1, then you print cascade is complete, else you print cascade is incomplete. Let's run it and see now. idea1.py, and then this is the initial graph where 4 and 1 are infected, and this keeps running. So it shows the result at the end after 100 iterations, and it shows you that the cascade is incomplete. So this is the only result we are interested in. We needn't see all the intermediate cascades. So I just introduced this here because we'll be using it in the coming up programming screencasts. Let's get started with the first idea where we have to increase the payoff and see what happened. So I'll basically take this code and I'll just paste it in another file, and let me name it as idea1.py. Okay. Now one thing here, you see here, currently we are running this process manually. So this is our initial graph, right? Annex.draw, where we set two nodes to have, where we set these two nodes 3 and 7 to have this initial, to have this behavior A, and then we draw this graph, and then we recalculate the options, and then we again draw the graph. So let's automate this process. So what we'll do is we can actually put this thing inside a loop, right? This complete thing can be put inside a loop. So what will happen if I put it inside a loop? So while 1, I just keep repeating this thing. So every time so this process has now become iterative. So we start with some initial configuration, and then every node recalculates its options, and then it keeps drawing the graph again and again. So I'll just quickly show you. So if I implement this here, Python idea1.py, see what? So this is our initial graph, and then you see it will keep drawing it again and again and again, right? So we can see how the cascade is growing in the network. So currently the cascade dies at the first step itself, so we are unable to see anything. Okay, so what we'll do is we want to put a terminating condition here. When should my code terminate? So for that, when should my code terminate? When should this process end? So the process should end when a complete cascade occurs, whether for the behavior A or B. So if everything has adopted the behavior B, behavior A dies away, and if every node adopts behavior A, behavior B dies away. So in both of these conditions, the process should come to an end. However, there is one more condition where it doesn't converge to either A or B. The node keeps flipping. So it might be, it goes into an infinite loop. So what do we do for that condition is we keep a maximum iteration limit for 100. So we don't want to see this process beyond 100 iterations. 100 is actually a big number. So we put a terminating condition here. First of all, we take a variable flag here, flag equals to 0. And while we recalculate this flag. It will call a function terminate G, which will decide whether we terminate or not. And if our flag equals to 1, then we break. So this function terminate, it runs some code, and if the process has to be terminated, it should set flag to be equal to 1. And let's also take a variable count here, count equals to 0, and we pass count also here. And count should increase every time. Okay, so let's now define this function terminate G and count. Define terminate G count. What is this function going to do is, if all the nodes have adopted the behavior A or adopted the behavior B, we terminate it. So we take further two values, flag 1. Flag 1 is terminate _1, a new function, and it checks whether, so flag 1 is going to check whether all the nodes in this network have adopted the behavior A. All the nodes in this behavior in this network have adopted the behavior A. And it's actually very easy to check. So we define terminate _1 here, and here we have here we have a character C and the graph G. So what we are going to do is, we take again an indicator variable flag. What we do is, for each in G dot nodes, so everyone should have a behavior C. So as soon as we find a node, if G dot node each, as soon as we find a node whose action is not equal to C but something else, it means that all the nodes in this network doesn't have this behavior. We set F equals to 0 and we break, and we return F here. So you see, F is going to return a 1 only if all the nodes in this network have this behavior character C. So flag 1 tells me whether all the nodes in this network have this behavior A, and similarly flag 2 tells me whether all the nodes in this network have this behavior B. These are two conditions. And then we have a count also. So count should be less than 100. So what do we do is, if so we have three conditions. If our flag 1 is 1, or our flag 2 is 1, or our count value is greater than 100, rather greater than or equals to 100, what do we do is, we return 1, that you should terminate, else we return 0. Okay. And now also, okay, so first of all, let's execute and see what's happening. So we execute it. So we have this network where initially 7 and 3 have adopted the idea, and then this idea goes away, and you see what happened. 7 and 3 are infected, and then this idea goes away. Everybody here has adopted B, so the process stops.